Yeah, so I'm from the TJ Watson Research Labs in New York. I want to thank Sam and Peter for organizing this fantastic conference. This is my first time in London. I'm really having a great time, so thanks for having it here. I'm going to talk about OpenWhisk under the hood, try to give you some idea of the design decisions, what we did when we implemented, and some of the novel, I think, cool stuff we did in the implementation, which you might be interested in. So what is OpenWhisk? Hopefully you've all heard about it at the conference by now. It's a serverless platform. What is serverless? I don't have to tell you guys in this audience. I would define serverless as having these properties. It's for a platform for short-running stateless computations with transparent instant auto-scaling and pay for the resources you actually use. And OpenWhisk, like many of the other so-called functions as a service offerings, fits this. OpenWhisk, as you probably know right now, it's in open beta. It's an offering in IBM's Bluemix cloud. So it's for free. You can go and try it. Go to just search for Bluemix, which is IBM's cloud platform. You can go and try it for free. I hope some of you saw the presentation yesterday from Andreas and Michael giving a demo of what the UI looks like. It's also command line interface and other tools. Perhaps you also know it's an open source project. Right now it's on GitHub. It's also been, as you might have heard, submitted to be donated to the Apache Foundation as an Apache incubator project, along with some of our partners at Adobe. So we're hopeful that this will be an Apache incubator project fairly soon. So you can go look at the code. We open source a lot of stuff. It's also, I would say OpenWhisk is what I would describe it as a bit of a higher level serverless programming model. What I mean by higher level is it's not just functions. Those are not the only entities and objects you can manipulate, but all of the core, well, there's a few, package, trigger, action, rule are core. If you think of this as a programming language, these are first-class constructs. So first class in programming languages means it's something that you can name. It has a name. You can refer to it. You can store it in data structures. You can pass it around. It can live independently of other constructs. So in OpenWhisk, not just actions, which would be what are sometimes called functions in other platforms here, but also triggers and rules and packages are exposed, if you think of it as a programming language, as first-class entities. You can do higher level in the style of functional programming. So you have, if you were doing functional programming, you can do functional composition, you can do currying. There are analogs of that in the programming model. With packages, you can encapsulate functionality, you can extend it, you can bind parameters. So I'll talk about all this. This is actually, it's interesting not just for a user point of view, but also for the point of this talk about how we implement the system, because we actually implement some major parts of the system in Whisk itself. So we're big into dog food, and we're big into building, as I'll show you today in this talk, some of the major parts of Whisk are built in Whisk itself using these concepts. And so one of the things I want to get to in this talk is to show you what that means and how this works. So what I'm going to talk about today is basically two things. First, I'm just going to talk about the basic runtime system. What happens when you try to invoke an action in OpenWhisk? What are the steps? What does the runtime actually do? And then I'll talk about some of these metaprogramming concepts and show you how we build a few of the interesting features on top of the basic runtime using Whisk itself. So let's get right into it. The first thing, just to mention, as I said, it's a hosted offering in Bluemix, and it's also an open source project. So the open source project you can download, you can deploy in Vagrant virtual machines or in virtual machines of your choice. There are scripts to deploy it on things like OpenStack. So you can run the whole system, a complete system locally. What we deploy in Bluemix is we actually pull the open source code directly straight from master. So it's not like there's any fork and an internal fork and an external fork. What we deploy in Bluemix actually uses the exact core runtime system from the open source project. So what you see on open source there is pretty much exactly what we're running internally. The only thing that's different is internally we surround the core runtime with a bunch of platform services, which are not necessarily open source, to do things like monitoring, logging, billing, authentication, a whole bunch of security features, and so forth. So that's stuff which is internal. What I'm going to focus on mostly for this talk is on the open source part of the code, and in particular on the core runtime system, the execution, and then I'll show you some of the other features. So let's talk about the structure of the core runtime system. So the first thing to notice is it's a Docker-based microservices architecture. So we deploy, the system is structured into a bunch of microservices. The two main microservices, which I'll talk about in some detail, are the controller and invoker. We use a bunch of open source middleware, which I'll talk a little bit about for queuing and service discovery and things like that. Rely on a NoSQL database, CouchDB, for persistence, and basically use Docker as the deployment engine on top of VMs. So that's the basic structure of how everything is deployed. So let's talk a little bit about Docker for a moment, why we chose to use Docker. So when we built this, we started building this system about a year and a half ago. You know, Docker is very convenient for some things. In particular, in our experience, you know, if you just want to deploy and manage a bunch of so-called traditional microservices, so not serverless entities, but simply services which are going to be up there and running and need to communicate via REST APIs. You know, Docker is really a great technology for this. It encapsulates your environment and your dependencies. There are excellent tools for managing and deploying and restarting. And so if you're just building a sort of a traditional microservice architecture, I think, as many of you probably know, Docker is really a great technology just for managing the deployment and isolation and discovery of all these processes. We also use Docker as our container technology. So when you run an action or a function in OpenWhisk, you're running arbitrary user code. We need this user code to run in an execution environment which is secure and isolated from other users. So in fact, the way we do is each action will run in its own container, and we use Docker as the container technology for spinning up. So logically, for each action, you'll get spun up a container. Like other platforms, the runtime system will try to reuse containers to avoid some cold start latency. I'll talk about some of the optimizations we do to avoid cold start latency. But Docker is a nice technology for deploying these isolated, and as long as you pay a lot of attention to security aspects and so forth, it can give you isolation and give you a safe environment to run untrusted user code. That said, we're not stuck on Docker for this part of the system for the future. Docker has some architectural issues and performance problems which make it hard to build a really super high throughput engine using the Docker daemon that cycles through a lot of containers very quickly and so forth. So what we've been doing gradually is, as we find bottlenecks in the system, we've been dropping down from using the Docker daemon for certain operations like pausing and unpausing containers or inspecting network configurations, and dropping down to lower level LXC and other lower level container stuff. So I think we're not necessarily tied to Docker for the long term as a container technology. It's been useful for now. There's been a number of headaches and problems, and we're working through that, mainly in the performance issue and also in concurrency. So just for running user code where we can control the whole environment, we could, logically we can use any container technology that meets the requirements. However, there's another reason we chose Docker, which is for if you want to basically use binary code in your actions. So if you want to write an action which uses a C library, for example, you need to basically produce a binary compatible with your operating system environment and run the code there. And this is a problem in general. How do I produce binary code which will link and run correctly in the server-side environment? That basically means I need to have some compatible environment locally where I build my code, so when I upload it, it'll still run. So there's this problem of keeping a local environment and the server-side environment in sync and exactly the same and compatible. So this is exactly a problem which Docker solves. So besides just being a container technology, Docker also has the notion of a Docker file, or basically a portable description of an environment. And we leverage this as a way to describe, arbitrary binary user actions. So if you want to write actions in a language which we support natively, such as JavaScript or Java or Python or Apple's Swift language, you don't have to worry about all this. But if you want to write in a language which we don't support, and people have done this for things like Go and Scala and Haskell and so forth, or if you just want to upload binary things or use C or anything else, as long as you can encapsulate it in a Docker image and build a Docker image which obeys certain protocols, we can run and manage the Docker image as a Whisk action, as a serverless action. So a lot of users have found this to be very useful for basically for running lots of code and lots of actions, which you might not anticipate, but as a service provider, but as long as you provide them a way to describe and upload their environment, and this is what we use Docker for. So for this particular use case, Docker is really great, and I think that what you need basically is a standardized image format, and I think Docker has won as the standardized image format for describing these kinds of things. So for that, Docker is really a great choice. So let's just go through the basic core runtime. So in the command line interface, if you're invoking an action, you'd say whisk action invoke, hello. We just walk through in 8 steps what happens when you do this. So first, basically this gets translated to a post to a REST API on a particular URI. Like many systems, first it'll get routed to an Nginx instance. We use Nginx to do the SSL TLS termination. We can use it for load balancing, and especially we use it for blue-green continuous delivery. So many times when we update the system, we'll have a blue system running, spawn up a green system, and do an atomic swap at the Nginx level. And this is how we can do, of course, rolling updates with zero downtime, just like many other systems. So Nginx, obviously is a great front-end routing technology. So the request goes through Nginx, it does the SSL termination, and then passes it to a service which we call the controller. Controller is the brains of the system, and I'll describe many of the next few slides are going to talk about exactly what the controller does. So the controller is a service, it's a web server. It's implemented in Scala. It heavily uses the Akka actors library inside Scala. It has a number of client libraries to interact with other services like Kafka and CouchDB and Consul. We'll talk about that. And then there are a number of user-written components which we wrote, which include caching and authorization and load balancing and data models. I'll talk about these in a little detail as we go through. Of course, if you're familiar with Scala, there's a domain-specific language in Scala called Spray, which we use for now for basically as the web server front end for doing the routing. We might move eventually to, there's a new way of doing this in Scala called Akka HTTP. It's not quite ready yet. I'm going to talk a little bit about why we chose Scala. This actually was a somewhat controversial choice inside this when we decided to go with this. Not controversial among the original development team, but later on when we brought on a bunch of new developers, we heard the protest, our developers don't know Scala, it's hard to find skills, we really love Node.js, things like that. So originally all the prototypes of the system were built in Node.js and using Express and things like that. And our feeling was, Node.js, it's really good for prototyping something, for bringing something up quickly. But if you want to build a really bulletproof, robust piece of server software, I know this gets into language wars and language philosophy. Our religion would say if you do this in Node.js, you're crazy. Especially if you have a system where you're going to have a bunch of developers hacking on the same code, you want to have an agile methodology. There's a lot of people refactoring, doing a team refactoring and changing an untyped language. We found we was just running into many bugs, and it's really, static typing really made many of these problems go away. If you're not familiar with Scala, it has a very strong static type system. Many cases when you're programming in Scala, you'll find that once you get your code to type check, it may be pretty close to correct. Basically, the type system eliminates whole classes of errors, and so it makes refactoring much easier in the sense that, yes, you have to get your code to type check, but once you do that, a whole bunch of bugs which you otherwise might have dealt with just can't happen because the type system ensures they can't. We also like Scala because it has pretty nice concurrency library, especially with the actor model. And the final thing, which was the really pushed us into running on the JVM, was the support for Kafka, because the Kafka libraries are officially supported on the JVM, and those were the most stable. So in a nutshell, once we switched to Scala, we've been extremely happy with it. This was our first major Scala, for most of us, our first major programming project in Scala. And in retrospect, my opinion is that was one of the best decisions we ever made. So very happy with that. All right, so let's talk about the controller. So the controller, a request has come into the controller. It's dispatched it and routed it. The first thing we're going to do is authentication and authorization. So we'll have a user database stored in a NoSQL database, which our system assumes for now CouchDB, or Cloudant, which is IBM's hosted CouchDB service. So one thing I should note in general, anytime I say, we're using the database, we do try to cache everything locally in process. So when we talk about performance and we talk about the latency of the common case, most of the time on the common case, we'll have 0 database operations in the common case, where every single so-called database access will be served from the cache. The other thing to talk about is the authorization. In the open source code base, there's a local authorization model, but it also has a extension point, if you will, for a plugin to talk to an external authorization. So of course in Bluemix, the open source code authorization delegates to a plugin which does authorization through the Bluemix IBM's authentication models internally. So basically the code base is structured so that you can plug in authentication if you want to do your own deployment of OpenWhisk in this sense. All right, so once you've authenticated, determined who this user is and that they have privileges to do what they want to do, they're invoking an action, so we have to go to the database or the cache again, find out what this action is, find out what are the resource limits, check whether at the given point of time, based on policies, that we're going to permit this invocation. Once again, this is primarily checking state. One note about just the implementation. So the code for most actions, not the Docker images, but everything else are stored as documents in a NoSQL database. If there are binaries, for example, if you upload a zip file with a bunch of dependencies, they're stored as blobs in an object store, which can be attachments or attachments in CouchDB in particular. All right, so we're still in the controller. We've got an invocation. We've authenticated. We've checked the action. We've decided that okay, we're going to go ahead and allow the invocation. Next, we have to decide where we're going to execute this. So there's a component in the controller called the load balancer. I should mention, if you go to the open source code base and look for these kinds of things, it's not hard. So like load balancer, search for load balancer.scala, and you'll find all this code. So the load balancer, we're in the controller. There are a bunch of slaves out there. We have to decide where are we going to run this action, what slave are we going to run it on. We leverage console heavily for service discovery and health check and monitoring. Console, if you're familiar with it, is from HashiCorp's open source software. The core of console is a sequentially consistent key value store. It's replicated, which gives you a false tolerance. It also has a bunch of built-in utilities, which we leverage for health checks and monitoring. So the load balancer will check with console to determine which slaves are available, which ones are overloaded or not, and where would be an appropriate place to execute this action. Once a controller decides where to execute the action, it's going to post a request to Kafka. Kafka, again, open source software. It's a very widely used, very high throughput, reliable, that replicated with good reliability features, messaging system, queuing system. So mainly we use Kafka for queuing. In case our system has more offered load than idle resources at the moment, basically we need to queue up work for future execution if there's not a slave idle ready to run it at this moment. And so basically Kafka we leverage for a fault-tolerant, distributed, high throughput queuing system. And we've been very happy with Kafka. Kafka is been very bulletproof, very reliable. Other than with the client libraries, I don't think we've had any problems with the server-side aspects of Kafka at all. So I should say we don't use Kafka really as a pub subsystem. We really use it for point-to-point messaging, which we encode via topics. So you could imagine building a serverless system where the load balancing is in fact delegated to a pub subsystem like Kafka. That is, you can imagine just putting a message on a Kafka queue and the next free slave could pick it up and run it. We chose not to do that at the moment because we want to apply a little more intelligence in the load balancing, so we want to take control over exactly where work is scheduled and things like that. So we really just use Kafka. If you see in the system, messages are always given a topic, which basically identifies the receiver of the topic. So we'll pick the exact slave VM where we want to execute this, send a message to that slave VM through Kafka, and it'll get there. Once it gets to the slave VM, it's picked up by a component called the invoker. So if the controller are the brains of the system, the invoker is the muscle. This is where the real work of running all the user code is going to get done. Like the controller, the invoker is again a service written in Scala, using Akka actors for the concurrency model, and uses a number of other open source utilities. The main thing the invoker is going to do, so we're on a slave VM, and the invoker is doing container management on the slave VM. So it's going to, the invoker picks up from Kafka a request saying, I need to run this action. Now the invoker's job is to find locally, do I have a container which is appropriate, already set up and running, which is appropriate to run this action? If so, I can dispatch the action directly to this container. If not, I have to spin up or otherwise provision a container, which I'll talk about in a moment, to run the action, and so forth. So this is really a large part of so the code is in containerpool.scala, which you can go and look at in the open source code base. And basically, this is it's a container manager. It will garbage collect containers. It will allocate containers. It's like automatic memory management for containers. Talk about cold start versus warm start. So remember, we're going for a low latency here. In our experience, doing a Docker run on one of our standard containers can take 200 milliseconds, which is too slow even for what we could call cold start. So for most kinds of actions, what we'll do is we'll maintain stem cell containers. So we'll pre-allocate a pool of containers which are running, but are simply not yet bound to a particular piece of user code. They're ready to go, but they're not yet specialized for a particular action. So the way these containers which are running run a little web server there. So in order to bind, to bind a container to run a particular piece of user code, basically the invoker will do a post to the /init route and inject the code into the container. At that point, the container is bound to a particular action. That container can be reused for future invocations of that action, but can't be reused for invocations of any other action. So at that point, we call it a warm container. And each time we need to use that container, the invoker will post to the /run route on the container to run an action. This is actually one of the most important for performance and tuning. This container pool management and everything is really one of the most critical parts of the system and where we spend a lot of effort. So it's something very important to get right and bulletproof and try to get the critical path down as far as we can. All right, so we've posted to run. We've run the action. When it's done, the container will return an HTTP response back to the invoker saying, I'm done. At this point, the invoker can go ahead and notify, if it's been a blocking invocation, it will go ahead and start off a process to notify who's waiting for this, that it's done. Asynchronously in the background, it'll start fetching the logs out of the container. Fetching the logs out of a Docker container can take some number of milliseconds, perhaps up to 100 milliseconds. So that's done asynchronously in the background. So it might take up to 100 milliseconds for the logs to be available through the logging API. Once everything's done and it's extracted all the logs from the container, it persists the results in the NoSQL database and marks the container as free and is ready for the next invocation. So pretty much that's the basic runtime of invoking an action in OpenWhisk. In our benchmarks, the 8 steps which I described, if it's all cache hits, in our benchmarking we see it being about 45 milliseconds. We can probably cut that down with a number of optimizations. And I encourage you, we do all our development and discussions out in the open. So if you look at our GitHub repository and you look at the current issues which are being discussed, there are a bunch of issues being discussed probably today as I'm speaking about optimizations being worked on to look at the latency and throughput. And so you can look at it, as I said, it's very much an open development process, and you can see exactly what we're doing and participate, and I encourage you to jump into those discussions if you'd like. All right, so that's the basic runtime. That's the basic functions as a service or actions invoking things. Now I'm going to talk about how we implement some of the things on top of this. So let's talk about feeds for a moment. If you used any of the serverless platforms, you're probably familiar with the eventing model. And most of the time in a platform, you can subscribe to certain limited class of events which are provided by the platform. Maybe you're waiting for events generated from an object store or from a vendor's queuing system, or events which are done by an HTTP post. That's all good, and it's very useful. In OpenWhisk, as I said at the beginning, everything is first class. So in particular, feeds are first class. So we don't distinguish in the programming model between, there's no such thing as sort of a privileged object store feed of events which the vendor provides. Anybody can create a feed, publish it, and use it, and it will be treated on par as a first-class entity and can be very convenient to use them. So the main point is you can write your own feeds and publish them and let people use them, and they just become part of the ecosystem. So what we're trying to go for here is making it easy for an extensible ecosystem where anybody can start to provide packages which provide actions and feeds which other people can use. And in the open source community, there's been a bunch of people who have implemented their own feeds. There's a lot of ways, a lot of architectures you can use to implement feeds, and if you go to our documentation, we list most of the common design patterns. Let me walk through the simplest one, which is just integrating with a webhook facility provided by someone else. So let's use GitHub webhooks as the example. This is a package. I'll show the URL, or you can find it. So we have a GitHub package in OpenWhisk, and this is, so basically what I'm saying is I want to subscribe to events coming from my GitHub repositories. In OpenWhisk, these will turn into triggers. I'll write rules in OpenWhisk which say when this trigger happens, when this event is generated from GitHub, I want to call these certain actions and so forth. So what I want to talk about today is, and GitHub, the way this will be implemented is using the webhook facility provided by GitHub. So GitHub provides in particular an API which you can use to set up webhooks for certain kinds of events. So what I'm going to show you is how we build OpenWhisk code which uses this webhook API to build a feed and then expose it as a first-class object in the Whisk ecosystem. So let me just show you quickly some of the command line stuff of how you would use a feed from the command line. So the first thing you do is you would bind a package, so you would expose a package, and you would bind it to, which is effectively giving a new name to the package, which is bound with your parameters, which are usually things like credentials. So from the command line, here I'm saying I'm going to use the GitHub whisk.system GitHub package, except I'm going to create a binding to it, which I'm going to call myGit, and I'm going to bind it with certain parameters, which are my credentials and for my GitHub repository. Once you've created a package, you create a trigger. So I say whisk trigger create, and then I say my get trigger. I say use this feed, and here's a parameter, in this case saying I'm interested in push events. And what happens under the covers, which I'm going to show you how to build, is that when you call whisk trigger create, under the covers there's going to be something which is going to negotiate with the webhook API from GitHub to basically set up a webhook which is going to post to a URL which Whisk is going to be listening to, and turn those into triggers, which then flow in as events into the OpenWhisk ecosystem, and you can then associate with rules and actions. And so, and then that would be the next step. Once you have a trigger, my get trigger, I'll create a rule, in this case called R, which is saying when an event comes in on my get trigger, pipe it to an instance of my action. So let's talk about, what I want to talk about is how you would implement this GitHub trigger yourself. So as I said, if you saw in the previous slide, you're using the whisk.system GitHub package. That basically means we wrote it, and we published it under our namespace, which is whisk.system. But the point of this, what I want to go through, is that anybody could do this. So you and yourself, in your own namespace, could create a GitHub package and publish it, and it would be exactly the same as what we've done. You don't need any privileges or any special keys to the kingdom in order to do this. So let's talk about what this would do. So if you wanted to create as I said, the main thing here is negotiating with the GitHub webhook API to install and delete webhooks. So logically, what you want to do is, let's talk logically for a moment before we actually get down to code. You'd want to set up a REST API, a service, which basically provides CRUD, create, read, update, delete operations for feeds. So what you'd like to do is when someone says whisk trigger create, you'd like under the covers somehow for this to invoke a create feed operation on some logical REST service, which under the covers will go and negotiate with the GitHub Webhook API, create the trigger, set it up so it'll go to the appropriate URL. Do this all under the covers, though, so that from the user point of view of Whisk, all they do is Whisk trigger create. And then as far as they're concerned, they don't need to know about the implementation of GitHub. They don't need to know their Webhook API. They just know that, OK, somebody exposed GitHub events, and I'm going to use them. So logically, what we want to do is basically build a service which has this REST API, which encapsulate the negotiation with the GitHub Webhook API. So, all right. We have to, first of all, implement this REST API. So what's the simplest way to implement a, let me use some keywords, a short-running, stateless REST API. And hopefully you got the hint that we're going to do this serverlessly. So instead of actually standing up a service and doing a REST API, we're going to just stand up a serverless action, which effectively provides the features of this REST API. So we create an action. It was called GitHub feed, and I'll take parameters, and one of the parameters can be the verb, create, read, update, delete, and then the rest of it is off to the races. So this action, which is a serverless action running in OpenWhisk, will do the negotiation with the GitHub Web API, set things up, and return. So what happens under the covers is when you do a Whisk trigger create and you give it -- feed, this is really syntactic sugar to say, when you create this, this trigger, under the covers, Whisk is going to invoke an action by this name. It's going to invoke my Git webhook. And it's going to pass this action. This action, we call it a feed action. And it's basically, logically, it's this REST API to create a feed, hook it up to OpenWhisk, set up triggers and things. So, under the covers, the Whisk system will invoke this action, pass it the appropriate parameters, such as the lifecycle event, in this case create, obviously for delete and others, there'll be other lifecycle events. Give it some parameters needed to know, like the trigger name, where should these events be redirected to, any authorization, and so forth. And that's it. And then, so if you write this action, so basically writing a feed basically boils down to writing an action. And then you encapsulate this action in a package. So as a user, you can create your own Git package, my Git package. You can, if you write this action, you can create my feed action in my Git package. And then simply you say, I'm going to share this Git package. At that point, you've exposed in your namespace my Git package. And now anybody, if you've made this public, anybody else who's running in Whisk can now use your Git package. And basically, as far as they're concerned, you've added the Git feed to the OpenWhisk ecosystem, and it's a first class. It's out there for use, just like any other source of events in the ecosystem. So the point here is, we've gone to a lot of effort to try to make it an open process. We're very much inspired by the npm package ecosystem. So if you're programming in Node, you can pretty much go to npm.org and find a package which pretty much does almost anything you could imagine. And ideally, we'd like to make it just as easy to start to expose event producers and consumers in an OpenWhisk ecosystem. And this is some of the technical design decisions we made to try to make it as easy as possible to do this. OK, I've got about 5 minutes left. Let me go to something a little bit more. Another instance of metaprogramming, which is building a debugger for OpenWhisk. And again, we're going to build this debugger in OpenWhisk. So let's talk about the use case and motivation. So suppose I have a trigger running in the cloud. It's invoking an action. In this case, my action is a sequence, so it's going to call A to B to C. So if I'm a developer, ideally, what I'd like to do is debug this. I'd like to just go into my debugger and set a breakpoint on B, and then get notified when B runs, drop into a debugging session, and then inspect it. Now, one thing to be clear is I don't want to just run my actions locally. I don't want to, basically what I want to do is have to set up mocks. I don't want to have to mock. So these triggers and these events and some of these actions are just things running in the cloud, coming from services, coming from who knows where. There's a bunch of events. And I want to go beyond simply mocking all of those into a local environment, but I actually want to debug live. I want to see what is going on right now with my code running in the cloud. Something strange is happening. I want to go in there, do a breakpoint, look at what's going on, and then back it. And I don't want to spend the time to actually set up mocking objects or things like that. At least that's the use case I'm going to describe today. So the question is, how do you do this? This is somewhat in contrary to the whole design of the serverless runtime. As I described earlier, the whole serverless runtime is designed so that these actions which are running are stateless, short-running actions. It's not designed for you to set up a long-running session that you can connect to via some debugging protocol through untold layers of firewalls and security and things like that. It's just not, debugging is a long-lived process, and ideally, I think, a lot of developers, myself included, want to do the debugging as locally as we can using our local tools. And so we have this problem here is that we're really running cloud code, but we want to debug it locally, and we want to make it as easy as possible to debug locally something which is faithful to what's running in the cloud. So I'll give you a preview. We actually have a debugger which you can use, which does this. So just a little demo here. So this is showing that I have an action running in the cloud. I was showing the output of that action live. So here's a view of our debugger. You start up a debugger. I'm going to look at this sequence, as I described, sequence 4, which has 4 actions. I can invoke it directly from the debugger. That actually invoked it in the cloud and got the result. And if you go back to the console, you'll see that that was invoked. So now I'm going to do exactly what I described. I'm going to say I want to attach to this action A3, which is running in the sequence. Okay? And then what I want to do, I look at it, we see the action sequence. Now it tells me that I've got a breakpoint there. And then boom, it so happened that that just ran because an event in the cloud was triggered, and I got notified, and it opened up a local debug session. So here now I'm actually running a Chrome debug session, and it's jumped into my action code. And now I can do anything I can do in my local debugger. Particularly in this case, I can go in, I can modify parameters, I can inspect things, I can continue and run. The result of this will be pushed back to the cloud. So back in my regular cloud console, I see what was actually running in the cloud, and actually reflects the changes I made locally, and they're running, and so forth. So that's the desired end goal. So let me tell you how we build this. So if you're going to build a debugger for a normal language, for a C program or whatever on x86, the way debuggers work is you go in when you say, I want to set a breakpoint at a particular point, what the debugger will do is it'll go in and it will rewrite the assembly instruction at a particular address to a jump. This jump will go to a debug subroutine. This debug subroutine will push the return address, run some debugging code, and when it's done, it will return to the subsequent instruction. So this is how debuggers have been built since from my whole lifetime. And so this is the basic concept. What does this mean in a serverless environment? So let's go back to the example. What we're going to do is when I say I want to attach to an action B in a sequence, all right, I'm going to create an action which effectively does the jump. So this will be an action which says when I hit B, instead of executing B, jump somewhere. I'll do a continue action, which is basically the return statement. When I'm done executing B, return back to whatever I was going to do. I'll hook up these jump and continue actions into rules. So instead of my original rule, which is saying run A, B, and C, I'll have one rule, which I'll call RJ, the jump rule, which is run A when I get to B, jump somewhere. I'll have another rule, which is continue, which is when I'm done with B, do a continue, and then run whatever else I would have done. These are all running, again, in the cloud. What's not running in the cloud will be a local debug broker. I'll discuss this in a minute. So the flow of what actually happened in the demo, what I showed you, is the Whisk tool, when you said attach, it looked at your code, it looked at your sequence, a huge introspection to figure out what your sequence was. It deleted it. It can inspect all of these entities because they're first class and represented it. It created new rules and triggers, basically to represent this, these jump and continue things. So when you get to the jump action, when you started up, I should mention, when you started up the debugging, the debugger locally, what happened was actually you're running a process locally which connected, which basically registered itself saying, all right, when you have this jump action, send the data to me, I'm ready to receive it. So the jump action was then configured to send both the action code itself as well as the state live to their local debugging thing. The debugging broker then will send all the state and all the information to a local debugger, Chrome, or we have support for Swift and Python debuggers. You can go ahead and do your debugging. At this point, effectively in the cloud, you could think of this as being a long-running action. It's just, we're doing local debugging. Everything at this point is happening locally. When we're done, the local debugger sends it back to the broker, who then notifies the cloud saying the debugging is done, please continue, and that's it. So that's really pretty much the architecture of the demo I showed you. So what I think is the cool thing about all of this is that this was all done completely in user code. There wasn't any privileged system access, so basically a user just could do this and did it effectively. All in user space. All you have to do is be able to introspect your actions and rules, delete them and rewrite them, install them, and then write a little debugging program locally. So this gets back to the theme I wanted to say, is if you have first-class entities, if you have some of the ability to introspect and manipulate your triggers and your rules and your actions and your packages locally, then you can do a lot of things really cool. You can start to build tools and debuggers and libraries and frameworks on top of this very elegantly. So anybody in this room could have written this debugger. You didn't need to work for IBM or have any special resource. And so I encourage you to go and look at the GitHub repository and see all the code and try it yourself. So I'm pretty much done. What's coming next? What are the future things? I could give you a long list, but really what I want to say is you tell me what's next. As I said, I hope I've given you the impression that we've done all this open source, we've done all this in the open, we've tried to design APIs that's all in the open, and really what we want is for this to grow as an open source, open community, and we think we've provided the foundation that makes for a very extensible, fun to build, fun to play with system. When I made these slides, there were 106 repositories on GitHub which had the string OpenWhisk in them, so I encourage each of you to start playing with things yourself and let us know if you build something cool, because that's what this is all about. Thank you very much.